So, in critical value approach we go for f calculated value with respect to f alpha value. As you know, alpha is basically your significance level, right. So, usually we take significance level to be 5% or 1% or 10%, right. So, f calculated value is greater than f alpha, that means it falls in the rejection region and hence the null hypothesis will be rejected. So, in order to calculate this we go for what is called as f table, right. So, essentially these days we do not go for f table, its value is available in the Excel calculation, or you can always use the p value rule, that is p value less than or equal to alpha value, reject the null hypothesis, but this also is necessary for you to understand. And you go for f table will ask for numerator degrees of freedom and denominator degrees of freedom. So, for numerator means this is the degrees of freedom associated with MSR, denominator is the degrees of freedom associated with MSC, right. So, for this p, that is number of independent variable, becomes your numerator degrees of freedom, denominator degrees of freedom is n minus p minus 1, right. So, you can remember this, and this all these things you can verify in the ANOVA table. So, this is a condition for f test, and giving this for our example, because our example has got two independent variables, and accordingly we have defined the null hypothesis beta 1 is equal to beta 2 is equal to 0, or at least one of the parameters is not equal to 0. So, after calculating for alpha is equal to 0.5, degrees of freedom is 2, right. So, that means f is equal to, if you remember, MSR by MSE, right. So, R is degrees of freedom. So, number of is 2 independent variable, here n is equal to 20. So, that is n minus p minus 1, that is 20 minus 1 minus 1. So, which is equal to 18, right. So, n minus p is 2, so and hence it is 17. So, 2 is the numerator degrees of freedom and denominator degrees of freedom is 20 minus 2 minus 1, which is 17, right. And as per the alpha of 0.05, the f value is 3.59. Now, for the calculated p value MSR by MSC, right. So, we use degrees of freedom 2, 17 and the alpha value to arrive at the f alpha. Now, f calculated we need to calculate by the from the ANOVA table, right, which is your MSR by MSC, or otherwise our usual method is, if p value is less than or equal to alpha value, then reject the null hypothesis, right. So, this is a famous acronym that I usually tell to the students, plan R, right. So, R stands for copyright or something you can imagine. So, plugging in the values, right. So, this is ANOVA output for our example, plugging in this value, this is your MSR, this is your MSC, and we get f calculated to be 42.76, and this is basically your p value, right. So, E column is your f calculated or f value from the table, f value from the calculation, and this is your p value, right. So, substituting this I get the value of 42.76, 42.76 is way more than 3.59, right. So, you can imagine like this. So, I set the boundary condition for the f is little right skewed test, right. So, f alpha is coming something like this here, which is 3.59, and this is my rejection region, reject H naught. So, obviously 42.76 very much falls inside the rejection region, right. So, 42.76 and hence I reject the H naught. Same will be complemented in terms of p value also, p value is less than or equal to alpha value. So, if you look at it, the p value also here is 2.32 into minus 10 power minus 7. So, obviously, it is very less than 0.05. So, since p value is less than the alpha value, we reject the null hypothesis. So, which is a good news, that means there is a overall model fit. Moving on. So, now that we know overall model fit, Now we are going for individual variable significance. The individual variable significance we do it using t-test. How do we do it? This is the hypothesis for it, right. So, individual variable significance means the coefficient should not be 0, right. So, beta I is not equal to 0 is a null hypothesis, and alternate hypothesis is beta I is equal to 0. Then this is your test statistics, right. So, bi, which is the coefficients that we obtain, that is estimates of beta I divided by the standard error. The same rule applies, p value less than or equal to alpha value, reject the null hypothesis, and since it is a two tail test, so accordingly the two regions comes over here, right. So, this is your positive t alpha by 2 and this is your negative t alpha by 2, and both these regions are, this is positive t alpha by 2 and both these regions are calculated as rejection region, right. So, this is either you fall here or this side, both of them calculated as a reject H naught region, and t distribution here has a degrees of freedom of n minus p minus 1. So, testing for this individual significance with respect to this our example. So, we get this degrees of freedom as 7, which is n minus p minus 1, right, n minus p minus 1. So, n is equal to 20, number of independent variable is 2 minus 1 and hence 17, right, and then we calculate t at 5%, right. So, alpha, if it's alpha is 5%, at either side it gets distributed, right. So, total alpha is 0.05 and this side alpha will be 0.025 and this side alpha will be 0.025, right. So, that is what is t alpha by 2, right. So, the value of t alpha by 2 is 2.11 and then the t value is very much greater than 2.11 and in this case t value is very much less than minus 2.11, right. So, here it will be positive value, here it will be negative value. So, either way if you see it, it falls in the rejection region, and p value is also less than or equal to alpha value in this case. So, and hence you reject the null hypothesis, which is your plan R. So, either way we end up saying that beta I, the coefficients is not equal to 0. So, we reject the null hypothesis, which is our good news. So, overall model significance is good up to our liking, and individual significance is also good up to our liking. So, going to the regression model. So, this is intercept, this is your independent variable 1, this is your independent variable 2, right. So, applying the hypothesis for each and every independent variable, you get a t stat and then you get a p value, right. So, essentially stay with the p value for all practical purpose, essentially it throws in the p value, right. So, going for critical value approach for understanding purposes what is this used, but for all practical purpose whatever you need to remember is p value less than or equal to alpha value, what do you do? You reject. What do you reject? You reject the null hypothesis, right. So, plan R, always remember that. So, now if you look at it, this is a p value is 1.9 into 10 power minus 6 and alpha value usually we take it as 0.05. So, obviously if you look at it, p value is very less than the alpha value and hence reject the H naught. So, that means what? Experience is significant. Test score, if you look at it, again 0.003 in terms of test score, p value is 0.005, even if you take 5, then p value is this and alpha value is equal to 0.05, and here also p value is less than alpha value, hence reject the null hypothesis. That means test score is also significant. So, this is again a good news for us, because for this regression which is salary as a dependent variable, it says salary is dependent or being explained, variation in the salary is being explained by the experience the person has and the test score that he or she has scored in the aptitude test, right. So, T test and p value used for individual significance of the experience. So, here they explained only experience, but of course, test score is also significant here. Now, this is for the test score and the previous slide is for the experience. So, this is a calculation for T calculated, right, and then this is of 7.07 and 3.24 we got it. If you look at it, 7.07 and 3.24, how do we get the T stat? Using this formula, right. So, beta coefficients divided by the standard error. There is a separate calculation for standard error. So, we do not need to worry about this now, but get an idea of how they are related. So, both independent variables are significant, which again is a good news for us.